Today we are going to look at the particulate nature of matter. This is a key concept in chemistry because it tells us how particles usually behave. So let's get into it. Now, matter is anything that occupies space and it also has mass. So anything that occupies space and also has mass is what we call matter. Now, this matter is actually made up of particles. Particles are actually the units of matter. Now, these particles can be atoms. Now, an atom is the smallest particle of an element that can take part in a chemical reaction. The other type of particles is actually molecules. Now, molecules are the substances formed when two or more of these atoms are chemically combined or chemically bonded. So when you combine two or more atoms, you're going to get what we call a molecule. Now, the other thing that you want to be familiar with is actually a mixture. When you're talking about a mixture, this is something formed when two or more substances are physically combined. So when you mix two things physically, not chemically like in the case of molecules, but physically combined, you get what we call a mixture. So for example, air is a mixture of different gases. Why? Because you can get this gas and that gas and physically combine them. Now, the other type of particles apart from atoms and molecules is actually ions. But we're not going to discuss ions just now. I think we'll talk about them more when we deal with chemical bonds. The next thing that I want you to understand now is what we call the kinetic theory of matter. So the kinetic theory. So what does this mean? Now, the kinetic theory states that matter is made up of tiny particles which are in constant random motion. Now, you can think of it like this. Let's say we have a container, and then in this container we have different particles. So let's just say that we have these particles. These particles are in constant random motion. Now, particles usually possess the type of energy which we call the kinetic energy. Now, this word kinetic is dealing with movement. So it is the movement energy. When we talk about kinetic energy, we are talking about the energy possessed by particles which enables them to make movements. So this kinetic shows movement. So if you try to increase the heat here or the temperature, these particles are going to absorb the kinetic energy. Each of them is going to absorb the kinetic energy, and that now increases their speed. They're going to start moving rapidly within the same container. So as they move, they collide against each other. So particles collide with each other and with the container walls here because they're just moving randomly. The more you increase the temperature, the more you increase the kinetic energy of particles. Now, these particles also have the forces of attraction between them. These forces of attraction hold them. So if you attempt to break these forces of attraction through the application of heat, you're going to see that these particles are now going to start moving rapidly because those forces that are holding them together are no longer there. So just make sure that you understand those concepts. Now, matter exists in 3 states. So let's look at that. The 3 states of matter are solids, liquids, and gases. Now, let's make sure that we understand this, and please pay attention to this because chances are that you'll be tested on this during the exam. So let's draw the box showing matter in a solid state. Remember that matter is made up of tiny particles, or rather particles. So when you're demonstrating the state of matter in solids, particles are arranged in this way. So these are the particles. And the first thing that you will notice here is that these particles in solids are closely packed. They are closely packed. Notice that you don't have enough space between them. Not only that, notice that solids have a fixed shape. Fixed shape. The reason is, if you take the ice block, you notice that it is almost impossible to change the shape of a solid substance. And because it cannot easily be changed, that's why solids usually have a fixed shape. But they also have a fixed volume. Remember that volume is the space occupied by an object. So when you're talking about solids, notice that the space occupied by this object is fixed. It is not going to change unless something starts to take place, like melting, where you see that a solid substance starts to change into a liquid substance. Now, because of this, you realize that solids are actually incompressible. This means that you cannot easily compress a solid substance. You can get any brick or any solid substance and try to compress it. You see that you actually fail to do that. Now, when you're talking about the movement of particles, when the heat is applied to a solid substance, notice that because the particles are closely packed, it is quite difficult for them to make a movement. So that's why particles actually vibrate. They usually vibrate in their fixed positions. So let's make sure that we understand those points carefully. And also, when you're talking about density itself, of course, you know that solids usually have high density. So those are some of the properties that you want to be familiar with when you're dealing with solids. Now, for liquids, this is how a liquid substance looks like. So we're going to have particles like this. And the first thing that you will notice is that there is a difference between the arrangement of particles in solids and in liquids. Because in liquids, particles are loosely packed. They are not closely packed, they are loosely packed. That's the first thing that you notice. The second thing is that liquids have no fixed shape. Why? Because the shape of a liquid can actually be changed. When, for example, you get water into a plastic, you can actually try to change the shape, right? But these liquids have fixed volume. Because remember, volume again is the space occupied by an object. So in this case, the volume or the space is not going to change. It is going to remain the same if you try to calculate the volume of a liquid. As long as some liquids have not leaked out, then probably you're going to have fixed volume. So liquids have fixed volume, no fixed shape, and they are loosely packed. And liquids actually are slightly compressible. because when you try to compress a liquid, to some extent you're going to compress it a bit, but not that much. When you're talking about the movement, when the heat is applied to a liquid substance, notice that because of the spaces here, there's some spaces left here, then these liquids can move actually to some distance. So they don't vibrate, instead they move over a short distance. So let's make sure that you understand that. Now, lastly, when you're talking about gases, particles in gases look like this. They are widely packed. Widely packed. Not only that, gases have no fixed shape and no fixed volume. No fixed shape and volume. I hope you can see that because the particles are just so loosely packed. Not only that, gases are highly compressible. They are highly compressible. For example, you can get some air and then put them into some plastic. You're going to see that they are highly compressible. And also, they move widely. They move freely because there are some spaces between them. So these are some of the properties of solids, liquids, and gases which you have to be familiar with, because you might be tested on the arrangement of particles, or you might be asked to draw the arrangement of particles in solids, liquids, and gases, or you might be asked to state the differences between these three states of matter. So make sure that you absorb this information and practice more. The next thing that I want you to be familiar with is what we call the changes of state. Remember that matter is made up of particles, and matter exists in three states: solids, liquids, and gases. So how do these states of matter change from one state to another? Now, here we are going to have solids. Here we're going to have liquids, and then here we're going to have gases. So if you remember the arrangement of particles, here we're going to have something like this. And then in liquids, we are going to have something like this. And then in gases, we are going to have something like this. So here we have solid, liquid, and then we have gas. Now, remember that these particles in solids and in liquids and gases are actually held together by some forces. So there are some forces between them. These forces hold the particles together. So the forces are actually called the intermolecular forces. So these forces hold the particles together. So when you try to compare the strength of these forces, you notice that in solids, they are quite stronger than in liquids, which are then quite stronger than in gases. The fact that in solids particles are closely packed is enough to show you that the molecular forces of attraction that hold these particles together are quite strong. Whereas in liquids, they are not as strong as those in solids, and in gases, they are the least strong. So when you apply some heat, what you're going to notice is that these particles, each of them is going to absorb that heat as the kinetic energy. This is going to cause these particles to start vibrating. But when they vibrate more, the energy or the temperature or the heat is going to start breaking the intermolecular forces of attraction that hold these particles together. And as soon as these intermolecular forces of attraction are broken down, this state of matter starts to change from being solid to being liquid. So it is going to start changing its state from solid to liquid. And this process where through the application of heat, matter changes its state from solid to liquid is actually what we call melting. Now, when you heat the liquid further, when you continue applying heat, you're going to see that these particles are even going to gain more energy and more kinetic energy such that they are going to evaporate. And when they evaporate like that from liquid to gas, the process is actually evaporation. So evaporation is the change of state from liquid to gas. Now, sometimes you can actually remove temperature from the liquid. Remember that when you remove temperature from the liquid, when heat goes outside, that means that gives an opportunity for the intermolecular forces of attraction between the particles to actually become more stronger, and the particles start to actually come close. In other words, when you remove heat from the liquid state of matter, you're going to have the opposite of melting, which is actually freezing. So freezing is achieved when you reduce the heat inside the liquid state of matter such that the particles come together and form this shape where they're closely packed. So the substance has moved from liquid to solid, and the process is actually called freezing. Now, evaporation, of course, is also called boiling. It's like when you boil some liquid, you see that there's some water vapor that is formed. So evaporation is also called boiling. But there's a difference between evaporation and boiling, which we will look at just now. Now, when you reduce the heat in the gaseous state of matter, when heat goes out, when this exothermic process takes place, you're going to realize that again the intermolecular forces of attraction are going to be strengthened, and therefore the particles in a gaseous state of matter are going to come together to actually form the liquid. So in this case, this process is actually called condensation. Condensation is the state or the process by which matter changes its state from gas to liquid. So when you liquefy something, when you liquefy a gaseous state or a gas, that process is actually called condensation. Now, there is the fourth process which I want you to understand, and that is when the substance changes its state from gas directly to solid without passing through the liquid, or from solid directly to gas without passing through the liquid. This process is actually called sublimation. So I hope you can define these terms, because you just have to understand them within the concept of matter itself and the states of matter, and everything is going to become much easier. But keep in mind, for the substance to change its state from solid to liquid, some heat has to be applied. When you have ice block, the reason why it turns into a liquid is because it absorbs more heat. That heat breaks the forces of attraction between the particles and then changes its state to liquid. And then when more heat is applied, the particles in liquid state of matter are going to absorb more heat, and this is going to break more forces of attraction, changing the state of matter into a gaseous state. And then you can also do the opposite, where you remove heat. When you remove heat, you have the reverse, where a gas is changed to liquid and the liquid is changed to solid. Now, let's look at the differences between evaporation and boiling. What are the differences that are there? Or do you think there are some differences? Well, when you look at the two, here we're going to have evaporation, and here we're going to have boiling. So what are the differences between the two? What would you say? Well, the difference is that for boiling, it takes place at a fixed temperature, because you know what we call the boiling point. So, for example, the boiling point of water is 100 degrees Celsius. When the liquid is heated up to 100 degrees Celsius, it starts to boil. But when you look at evaporation, evaporation actually takes place at any temperature as long as it is below the boiling point of that particular substance. So it takes place at any temperature below the boiling point. Now, the next difference that you want to be familiar with is that when you're talking about evaporation, evaporation actually takes place at the surface of the liquid. That means that when you have something like this, if this is the liquid, then particles have to evaporate from the surface here. The reason is because when particles gain more kinetic energy, they try to move rapidly. But since particles within the liquid are actually surrounded by other liquid particles, it will be quite difficult for them to actually make proper movements. But those at the surface, they don't have much obstruction, and so they freely escape the surface of the liquid. So just make sure that you understand that evaporation takes place at the surface of the liquid. But when you're talking about boiling, it actually takes place throughout the liquid, throughout the liquid. When you see water boiling, you see that there are bubbles everywhere. So it means that it is boiling throughout the liquid. In fact, that's another difference, because when you're boiling something, you have bubbles. Bubbles are formed, but when it comes to evaporation, no bubbles at all. No bubbles formed. So that's another interesting difference. So at least for now, we can look at these differences, and please try to understand them, because you might be tested also on that during your exam. Now, the next thing that we need to talk about is actually what we call the heating and cooling curves. So we're going to have the heating, cooling curves. Now, when you're talking about the heating curve, this curve actually shows how the temperature of the substance changes as it is heated over time. When you're talking about the cooling curve, you're talking about how the temperature of a substance changes when it is cooled over time. So let's say we have the heating curve here. Let me draw the heating curve so that you understand what we are talking about. And then here we're going to have a cooling curve. So here we're going to have the temperature. So here is the temperature. And then we're going to have time here. And here we are going to have time. Okay. So let's say the temperature is 0 here. And here we are going to have 10. And then here we're going to have 20. So let's use those numbers to help us understand this. So a substance might be heated like this. So this is showing solids. So let's use letter S. And this is liquid. And this is gas. So we have a solid substance. And when we start increasing the temperature from 0 here, now when the temperature is increased like that, remember that particles within the solid substance are going to start absorbing that heat. And so they will start vibrating in their fixed positions. So they'll continue vibrating like that. The more you increase the temperature, the more they gain kinetic energy and the more they vibrate. But when the melting point is reached at this point, this is the melting point of this particular substance. When the melting point is reached, that solid substance starts to change its state from solid to liquid. So notice that from here to here, you have the substance changing its state from solid to liquid. You also notice that during this state, the temperature actually remains the same. It is still 10 here. Why is the temperature the same at this particular point? Well, because the purpose of this temperature at this point is not to just enable the particles to absorb more kinetic energy, but it is actually used to change, to break the intermolecular forces of attraction and change the state of matter from solid to liquid. So that temperature is not intended to increase more heat at this time, but it is intended to change the state of matter. So it doesn't change, it remains the same. So let's just say that here we have point A, B, C, D. So this is D, and then E, F. So what you realize is that at point A, the substance is in its solid state. From A to B, this temperature actually enables the particles to absorb more kinetic energy. At point B, you have the melting point of this particular substance. So the substance from B to C changes its state, so the temperature remains constant. At point C, that is the liquid state of matter. So at point C, you have liquid. And again, the temperature increases significantly to make these particles in the liquid to absorb more kinetic energy so that they can move rapidly within a liquid. And when you reach point D, this is the boiling point of this particular substance, because this substance then moves from being a liquid to being a gas. And again, the temperature remains constant because it is used to change the state of matter from liquid to gas. At point E, you have the gaseous state of matter. And the more you increase the temperature, well, probably regarding basic chemistry, there's nothing that is going to happen at that point. So make sure that you understand this heating curve. It is showing how the substance changes its state when the temperature is being applied. And also pay attention to these areas where the temperature is not changing, because that temperature is used to change the state of matter instead of allowing the particles to increase their kinetic energy. Now, the same is true for the cooling curve. Let's say the temperature is 0 here, and then here we have 10, and here we have 20. So it's just the same thing. We're going to say, okay, this is the substance, the temperature remains constant, and then again it is increased, and then it remains constant, and then goes up like that. The difference is that since we are cooling, so we start with the highest temperature here. So the more we cool this particular substance, remember that we are not applying heat. In this case, we are actually removing heat. So when heat is removed, let's make sure that we indicate the numbers here. So this is still solid, this is liquid, this is gas. And here we're going to have, this is, let's say, point A, and then B, C, D, E, and then we're going to have F here. So what is going to happen in this case is that we start from the higher temperature and we are removing heat. The reason why we are removing heat, if you remember the kinetic theory, is because we want these particles to stop moving rapidly, to lose more kinetic energy, so that they can arrange themselves as close to the liquid state of matter as possible. So when we remove heat, through the exothermic processes, we are going to realize that these particles start to move slowly and the intermolecular forces of attraction between them actually get strengthened. So the temperature from point A reduces significantly to point B and then it remains constant. Why? Again, it is because that temperature, which is constant, is being used to change this gaseous state to the liquid state. So at point B, you have the gaseous state, right? So here we have a gas, and then this gas is going to be changed into a liquid. So by the time you reach point C here, you have the liquid state of matter. So when you have the liquid, again you reduce the temperature from C to D until this liquid is now changed to the solid at B. So from B, you just have the solid state just like that. So these are the basics of the cooling caves, and also you might be tested on this one, so make sure that you understand the key concepts and the differences between them. Now, what is the experimental evidence for the kinetic theory? So how do you demonstrate that the kinetic theory is actually a correct theory? Well, first of all, there is a principle that we use, because remember that when you're talking about the kinetic theory, you're talking about tiny particles moving constantly in a container or any substance that you might have. So the first thing that we need to look at is what we call the Brownian motion. Now, let me draw a box so that you understand what this Brownian motion is about. So let's make sure that so these are the particles, and then what you're going to realize is that So what you're going to realize in this principle is that when you observe under the cell microscope, you realize that there's some particles that are constantly moving in the box. Now, the reason why they are moving is because there are some invisible fast-moving particles that are colliding with these particles. And so when you observe the movement of visible particles under the microscope, you're going to see that they usually move in a zigzag manner. Zigzag manner. So this is what the Brownian motion is about. It shows that particles are clearly moving randomly in the container as a result of colliding themselves with the invisible fast-moving particles. So an example of this, I think, the practical example is when you wake up in the morning and then you open the window, you see that when the sunlight is actually entering into your room, try to look closely at the sunlight itself. You see that there are some dust particles that are constantly moving, and they are moving in a zigzag way. That is an example of Brownian motion, because the air particles that you cannot see are able to collide with these tiny dust particles. Hence, you see the movement of these particles. So that is an example of how you can demonstrate this experiment on Brownian motion, trying to prove that indeed the kinetic theory of matter is the correct theory. And this takes place in gases and also in liquids. You can do an experiment for both gases and liquids. Now, the next one is the experiment on the diffusion of gases. Usually for this one, diffusion of gases. And the gas which you use usually for this experiment is actually bromine. Now, bromine is brownish in color, and so what happens is that you might have something like this. Let's say you have a box, and this box is on top of another box, and then let's say you've sealed this box. So here you have air, here you have bromine gas. And so let's say that we have bromine here, and then when you remove this thing here that is blocking the two cups or jars, you're going to have something like this. You realize that you have bromine even on the top jar. The reason is because particles in this bottom jar are able to move from this face of a jar to another face, the top jar. The reason is the bromine brown particles are able to move. As soon as this is removed, they're able to move to the other side because they are making some movement. They have kinetic energy, which is enabling them to actually make movements from this area of a jar to another area. Hence, the result you're going to have is like this, where bromine is actually extended to every part of the jar, and you have the uniform gas inside the two jars. So that's an example of the diffusion of gases. Gases are able to move from the region of higher concentration to the region of lower concentration, as long as there is this concentration gradient. The other thing that we can look at is the diffusion in liquids. So what does that mean? Well, it's simple. Usually what we use is what we call potassium permanganate. This is very important. We use potassium permanganate to demonstrate the diffusion process in liquids. So how do we do that? Well, first of all, what we need to do is that we can have a jar of water like this. So here we have water, and then when we put, let's say this is potassium permanganate. When we add potassium permanganate to the liquid, what happens? You see that the first thing that you see is that it starts to dissolve. So it dissolves to some extent, but not throughout the entire liquid. But when you wait for some time, you're going to see that it spreads evenly throughout the liquid. So you're going to have something like this. So the color of potassium permanganate spreads throughout the liquid. This demonstrates that liquid particles are also able to move. They are able to move from the region of higher concentration to the region of lower concentration, as long as there is that concentration gradient. Just like also when you try to use ammonia, when you try to use perfume, for example, you see that when you open your perfume, you see that the smell is felt by some people at a distance. Why? Because the perfume particles are able to move from the region of higher concentration to the region of lower concentration. Now, this is the diffusion process. What do you think are the factors that affect this process? Because diffusion is essentially the movement of particles from the region of higher concentration to the region of lower concentration. What do you think are the factors that affect the diffusion process? So factors that affect diffusion. What would you say? Well, first of all, you have to understand that temperature affects the rate of diffusion. But how? Well, it's simple. Because remember that when you apply temperature, the particles are able to gain more kinetic energy, which means that they are going to make more movements. And since diffusion is the movement of particles from the region of higher concentration to the region of lower concentration, then as long as you have particles that are able to move rapidly, then the process of diffusion is going to be elevated. It is going to be faster. So indeed, when you increase temperature, you increase the rate of diffusion. Conversely, when you decrease temperature, you decrease the rate of diffusion. The next thing that we can talk about, the other factor, is concentration itself. Concentration gradient. What does it mean? Well, let's say that you have these two scenarios. So you have these two scenarios. So here you have perfume particles, and also here you have perfume particles. Which of the two, between A and B, in which category are you going to see the faster rate of diffusion? What would you say? Well, in this case, you're going to see the faster rate of diffusion in A. The reason is because you have the steeper gradient here. The higher concentration gradient is going to enable more particles to move from this area to the other area. Whereas in this case, you don't have a steeper concentration gradient. So the rate of diffusion is not going to be as fast as it is in this particular case. So indeed, when you have a steeper gradient, you're going to have a faster rate of diffusion. Conversely, when you don't have a steeper gradient, the diffusion rate is going to be slower. So just make sure that you understand those concepts because they are very important. Now, the other factor that affects the diffusion rate is actually the size of particles. The size of particles. Remember that when you have particles that are bigger in size or larger in size, they're not going to move at the same rate as particles that are smaller in size. In other words, the smaller the particles, the faster the rate of diffusion. I think it's just a simple concept, right? Because it also has to do with the relative molecular mass of particles. Now, we'll deal more with the relative molecular mass when we deal with the more concept. But that's just another important concept that you might be familiar with, that when the particle has larger relative molecular mass, it is not going to make a quick movement as compared to particles that have a lower molecular mass or relative molecular mass. So make sure that you understand those concepts. So having discussed this, I think we can now go ahead and look at some problems that we can deal with. So the first question is, define diffusion. What would you say? Well, diffusion is the net movement of particles from a region of higher concentration to a region of lower concentration. So particles are moving, they are making some movement, and as a result, you have what we call diffusion. Now, another important question which you can look at is, I want to ask you, how can you describe an experiment to show the random motion of particles in liquids? How do you demonstrate diffusion in liquids? What would you say? Now, remember, the key thing is you have to use potassium permanganate. Remember that when you get this potassium permanganate and then you put it into the beaker containing water, it is going to start spreading. The particles of potassium permanganate are going to start spreading throughout the liquid until you have the uniform spread of particles throughout the liquid. So that is just simple. How do you demonstrate diffusion in liquids? Well, you use potassium permanganate. You place it inside the beaker of water. You see that this potassium permanganate, which is actually purple in color, is going to spread. So you're going to see a purple liquid at the end. Initially, you have water. You put potassium permanganate inside water. Over time, you see a purple liquid because the particles of potassium permanganate spread throughout the liquid through the process of diffusion. So that's how you can demonstrate the diffusion process in liquids. Now, the other question is, which you might want to look at, is that explain why the smell of perfume spreads through a room. Imagine someone opens the bottle of perfume and then it spreads. Why is that? Well, again, remember the concept. The perfume particles are able to move from the region of higher concentration to the region of lower concentration. So there where you are, you open the bottle. That will be the region of higher concentration because you have more particles of perfume. But since other areas don't have these perfume particles, so these particles are going to move from where you are to the other areas. As a result, people are able to smell the perfume that you have. So those are some of the key questions that you need to understand.